In this video, we're going to do a brief overview of pi bonding and how it relates to the formation of double bonds and triple bonds. So first, you need to remember that whenever you have atoms bonded together with covalent bonds with sharing, they're all going to be attached together with the sigma bond, so with that direct overlap. So all atoms in bonds have a sigma bond there to connect them to each other. So that you're going to have that sigma bond there. Now, the thing is, once that sigma bond has formed, the orbitals can't overlap again. Like they'll only overlap that one time and they'll form one sigma bond. So each overlap is essentially responsible for one sigma bond, and that's it. They can't make more bonds there. So in other words, there can never be more than one sigma bond between atoms. So even if you have double bonds and triple bonds, the additional lines that you have there, they're actually not from more direct overlap. It's from a different type of overlap we'll learn soon. But there's only one sigma bond in the double bond and in the triple bond, and then the other part of it is going to be a different type of overlap that, again, we'll see soon. So therefore, if you have a second or third bond, they're not going to use a hybridized orbital. So the second or third bond must not use hybridized orbitals. So let's go take a look at an example. We're going to draw C2H4. We can actually see carbon over here. This here is C2H6. Let's do this first, actually. C2H6. So if we draw out C2H6, we have this like that. So let's draw this out. These are all single bonds here with one line each. And so if we look at the carbon, we'll see that the carbon is sp3 hybridized. And same thing with this carbon here, sp3 hybridized. And so between the two carbons here, this is made from direct overlap of the sp3 orbitals. And so this would be a sigma bond. And then all the other single bonds that we see there are also sigma bonds. So this is a sigma bond over here, sigma bond there, sigma bond over here, sigma bond here, here, here. So we have essentially 1, 2, 3, 4, 5, 6, 7 sigma bonds in this molecule. And that's because they're all single bonds. The sigma bond formed between this carbon and this hydrogen is going to be a direct overlap between the S of hydrogen and the sp3 of carbon. And we didn't have to draw that. We're able to do that shorthand now because we can figure out hybridization just by looking at the electron regions. Now that's with only single bonds. We have this direct overlap forming the sigma. That's what that is forming there. And then we didn't quite show it here, but if we want to show the bond with the hydrogen, there's a direct overlap between the hydrogen electron and the carbon sp3 over here. So we have, let's say, the sp3 electron there, and then the hydrogen electron over here. This would be the 1s of a hydrogen. And that's a direct overlap as well. That would be a pi bond, pardon my crossing here. This would, sorry, a sigma bond. So we have another sigma bond because it's a direct overlap again. Now, let's go take a look at something a little bit different. This over here is C2H4. If you draw the Lewis structure out for C2H4, here's what you'll find. You get a double bond between the carbons, and then you have your hydrogens over here. And what you'll see is now we have double bonds. Now, anywhere that you have a single bond, that's simply going to be a direct overlap, as we already explained, and that's a sigma bond that creates that connects them. Where you have the double bond, one of the connections is going to be sigma, so one will be a direct overlap, but the other is not going to be a direct overlap. The other one is going to be a different type of overlap, and it forms what's called a pi bond. So in a multiple bond, you have one sigma, and then the other lines that you have there, they're going to be pi bonds specifically. So here we have 5 sigma bonds, and we have 1 pi bond. And the pi bond is going to be made from an unhybridized orbital. It won't be from one of the hybridized ones. And let's go and just do the hybridization of carbons. So let's call this one carbon A. If I want to know the hybridization of carbon A, I have 3 domains, sp2, sp2. And for carbon B, I have 3 domains, sp2, sp2. So the sigma bond that's made between them is made from a sp2 sp2 overlap. So we would sometimes call this a sp2 sp2 sigma bond. If we were looking at the let's say carbon B hydrogen bond, any one of them, it doesn't really matter, we'd call that an sp2 s sigma bond, because it's made from an overlap between an sp2 of the carbon atom, and then hydrogen is simply S. So an sp2s sigma bond. So essentially, we studied this molecule, and we saw that in this case, there's 3 bonds occurring at each carbon. And so what that means is, therefore, the hybridized orbital of the carbon is sp2. So we went over that. Now the 3 sp2 orbitals are going to spread themselves out really far apart, or not really far apart to minimize repulsion, and that'll give them an overall shape of 120 degrees. So essentially, if you're treating each carbon atom like a central atom, you basically have a trigonal planar type of molecule at each carbon as the central atom. Now, these sp2 hybridized orbitals, they're going to be involved in the sigma bond formation. Now, you'll notice that I said sp2 here. Don't forget that p has 3 orbitals, right? Remember, you have a box like this. P has 3 orbitals. There's P, P, and P here. So that means there's a P missing, right? There's a P not participating in the hybridization process. So one of the P orbitals is left alone, which means that it is unhybridized. 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 And it's that unhybridized P orbital that's actually going to be helping to make the pi bond that makes the double bond. So the unhybridized p orbitals on each carbon aren't pointing towards each other, but are overlapping sideways. Let's see what that looks like in our image here. So here you have sp2, sp2, they're going to meet together and directly overlap. This is going to form the sigma bond within the double bond that we have. So that's going to form the sigma bond here. Now, here's what I want you to notice. You also have these ones here. This is a hybridized orbital as well. It's going to form a sigma bond between the C and the H, and then same thing here, a sigma bond between the C and the H. So all these sp2s have essentially been used up at this point. So all the orange, the 3 sp2 orbitals that were created, they're going to make all the sigma bonds. And then same thing for the other carbon. Now, what you'll notice, though, is that there's this one over here on each carbon. This is unhybridized. It maintained its regular P shape. Unhybridized, not part of the sp2. And these 2 unhybridized P's on the 2 carbons, they're actually overlapping, but not directly. They're overlapping sideways. So I'll do this as a dotted line because they're not like a direct connection, but they're overlapping sideways with each other, top and bottom here. So that's their overlap. And that sideways overlap, which is not very strong, it's still an overlap, that consists of the 1 pi bond. I know I made 2 lines there, but it actually consists of just the 1 pi bond. You have sideways overlap above and below there. That's the 1 pi bond that contributes to the overall double bond. So this is our pi bond here. And as I mentioned, this part over here is the sigma bond there. So the sideways overlap of the unhybridized p orbitals and each carbon, one here and one here, will lead to the production of the pi bond, which therefore leads to a double bond with our single sigma bond there. So a bond that's formed by the sideways overlap of orbitals, typically unhybridized orbital, is called a pi bond. So we've already known that, but now we're just formally writing it down there. So this is another image showing a pi bond here. You can see it from the molecule we've been studying. So this is our molecule here. The direct regions of overlap are sigma bonds. So this is a sigma bond, sigma, sigma. This is a sigma, 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 sigma. And the green ones I circled are basically all, so the carbon's sp2 hybridized, and the hydrogen is simply S. So they're sp2 sigma bonds with some direct overlap. And then there's also a sigma bond here. This is a sigma bond as well. This first direct overlap between the two carbons is the first connection you'll see there. That is also a sigma bond, but it's an sp2 because both carbons are sp2 hybridized. Sigma bond. Now, don't forget that because the carbons are sp2 hybridized, that means there must be a p orbital that was left unhybridized, and it's going to overlap as well with the other unhybridized p orbital of the other carbon. And so that's what you see over here. So here we have let's do it with a different color. Let's do this blue color here. So this is the unhybridized p of one carbon, the unhybridized p of the other carbon, and this parallel overlap here, this indirect overlap that's happening, not direct head-on, there's top and bottom, that consists of the one pi bond, So let's put them together here. Here's our pi bond, and then we have our sigma bond there. But the idea is that this other little bond region here is made up of that indirect overlap of the unhybridized p orbitals. It's weaker because it's not a direct overlap, they're not directly touching each other, but it still strengthens the overall bond compared to a single bond, which is only made up of the sigma. So that is how a double bond is made with the unhybridized overlap of a p orbital. If we can go to our visuals here. So this is just a visual that goes over that concept in a bit more detail, with some more definitions provided to you in case you need additional definitions and reinforcement. But you can see we have sigma bonds explained that are only within single bonds. And then within multiple bonds, you have one sigma bond only from direct overlap. As you can see, here are some sigma bonds that are forming. But then as soon as we jump into multiple bonds, within there, one is a sigma bond and the other is a pi bond, which is the indirect overlap made from unhybridized orbitals that are typically going to be p unhybridized orbitals. They're going to be p orbitals that are unhybridized. So within a double bond, you have one pi bond. Within a triple bond, you have three pi bonds, as we saw earlier. And so here you can see the formation of the pi bond in this molecule with a double bond here. You have the overlap over here and over here. Overall, even though it looks like it's two other lines being added, this is just one pi bond for the double bond. And then the other bond of the double bond is the sigma bond, which is a direct overlap between the sp2 hybridization of carbon. And again, you can see more images here. We're showing you the direct overlap, the sigma bond, and here we're showing you the indirect overlap of the unhybridized p orbitals, and that would be forming the pi bond that's part of your multiple bond. So here's our double bond formation, one sigma and one pi to make the double bond. You can see it with the orbitals here. It would be good for you to know how to draw this and also how to represent it here. Can you draw this and label what the different parts are, where the pi bonds are? If you can do that, that's a good first step to understanding how to do the hybridization process with multiple bonds. Here's our triple bond, just to show you what that looks like in an image. So a triple bond is made up of one sigma bond, but instead of having one pi bond, it's two pi bonds. And so you can see the sigma bond over here forming between the hybridized orbitals of the carbons here and here. So these are the carbons, okay? Sigma bond is right here in the middle. The pi bonds are on top and bottom here. You can see that there's two unhybridized p orbitals. So you have an unhybridized p orbital here on one carbon and here on the other. And then the other carbon has unhybridized p here and here. So each carbon has two unhybridized p orbitals, and they're going to do their indirect overlap that way. So you have indirect overlap between this p orbital of this carbon and this p orbital of the other carbon, and then you have indirect overlap of the p orbital of this carbon and the p orbital of this carbon as well. And again, these are unhybridized ones. And so because you have a pair of unhybridized ones on each carbon, you have sort of two regions of indirect overlap happening. So this would be the blue indirect overlap, and then this would be the red indirect overlap. So this is one pi bond, and this is the other pi bond. So in our triple bond, we have a sigma bond from direct overlap. We have one pi bond from the indirect overlap of the first set of unhybridized p, and we have another pi bond from the indirect overlap from the second set of the unhybridized p. So our triple bond has one sigma and two pi. And yes, it looks like four pi bonds, but it's not. This is one pi bond. This red segment here is one pi bond. And this blue segment is one pi bond because there overlaps from, this is one p orbital. This blue is another p orbital. This red is one p orbital, and this is another p orbital. So they're forming the pi bond together here. And this blue one is forming the other pi bond as well. So two pi bonds, one sigma bond. So we're going to take a look in the next video at how to represent the formation of pi bonds using energy level diagrams. We've done it with sigma bonds. Now we're going to do it with pi bonds.